In Chapter 12, we are really going to expand our view of functions past what we've used traditionally from algebra class and pre-calculus. And it's going to hopefully really blow your mind. It's going to be amazing. I really love Chapter 12. So we're going to talk about parametric curves first, and that'll be section 12.1, and then we'll move on to polar curves, which is sections 12.2 and 12.3. And then if we have time, we would do conic sections, which is 12.4. And all of these really expand our view of functions and give us different orientations, different patterns, different ways of viewing things. It's amazing. All right, so let's start looking at parametric equations. So by default in our typical everyday lives as well as our mathematical lives, we default to rectangular coordinates. So, you say head north 2 miles and then east 3 miles. Slope is rise over run, etc. That seems like football. Run the ball laterally and look for blockers downfield, etc. So you're viewing everything in kind of this plane, but you're viewing everything rectangular in x, y. But another great feature of this coordinate system is we can analyze curves in that xy plane and not just functions of one variable by parameterizing the relationship between the two coordinates of any points on the curve. For instance, so in algebra class, you were lied to. You were told that this picture is not a function. And that's true. I mean, it's not a function in x because it doesn't pass the vertical line test. It's not a function in y, not that that's something we really dealt with much because it doesn't pass the horizontal line test. But it is a function. It's just a function of some other variable, a third neutral variable called a parameter. So we introduce this third dimension. Most often it's time, but time is not the only way you can do this. So we have a third dimension. So time, t, is the most frequent one to think about. Well, it's t, and time is the most often application that we use for that. You can also use angle, which we usually use theta. And when we do this, we can see that this graph actually has another way of being. So this graph is the graph of x equals sine of t and y equals sine of 4t from 0, which is less than t, which is less than 2 pi. And of course, why look at it there when we can look at it in Desmos? Because Desmos will actually graph it for us. All right, so here it is. And you can see that by typing in a Desmos, what you do is type in a parentheses, and you type in the x, which is sine of t, and the y, which is sine of 4t. I've added this little component right here because I want the graph to be visual. Otherwise, if I take that piece out, it just graphs the whole thing, which I don't really want. So you can see, hopefully from this visual, what this is doing, right? There's motion to this curve. So it is a function. It's a function in terms of time, t. Right? It's not a function in x, it's not a function in y, it's a whole other kind of function, parametric function, as a matter of fact, of time t. Amazing, isn't it? And it's also pretty to watch. Now, of course, you can't draw. I mean, when you do draw, you draw with motion. But once you've drawn, the picture is static. It just sits there. So the way that we show that motion that's going through the curve is by putting arrows on a curve. So a parametric curve needs to have arrows on it. And that's not something that the computer does for you when it draws it, as I drew this with Desmos. It's something that you have to put in yourself. So it started here, it went up, it went down, it went up and around, came through here, looped down, etc. So then it went up, went down, and back up. There's a parametric curve. These are incredibly useful, supremely useful, and they are all over Calculus 3, like white on rice. It's because motion is what we're modeling here, right? So parametric equations are incredibly useful because parametric equations allow us to have a mathematical formulation for motion. It's adding a third dimension, which is amazing because that could be water going through a pipe or electrical current going through a wire, you see? It's almost like there's a lot of physics applications where this would be useful, yeah? Yeah. Yes, there are tons. And of course, physics and Calculus 3 go together hand in hand. All right, so then let's consider this some more. So it's the same curve we were just looking at, sine t, sine of 4t. So we refer to the equations sine of t and sine of 4t as parametric equations because they relate the two variables x and y through a third one. So these right here are the parametric equations. Okay? They relate the x and the y to that third variable t, which is called the parameter. So t is your parameter. And again, it's not the only one. It's the most frequent one we use, t, but you can also use theta. That's another frequent one. I mean, technically you can use all sorts of things, but t and theta are the most frequently used. All right, so we also need to specify, because a parametric curve is no good unless it has a specific domain, has specific values over which t exists, which is right here. So you have to specify those values, which for us was 0 is less than or equal to t, which is less than or equal to 2 pi. So you must specify your domain. That's a parameter, must be specified. All right, up to this point in your mathematical career, you've gotten used to talking about y is a function of x, right? So when they were saying that to you, they were saying, y equals f of x. That's what we would say all the time, right? So now what we're learning is that x and t and y of t are both parametric equations of t. The truth of the matter is that we lied to you. Your whole mathematical life, we say, oh, it has to pass the vertical line test, or it's not a function. That's not true. Oh, it has to be a function of one variable. That's not true. I mean, you learn about explicit versus implicit derivations of functions back in Calculus 1, and that still holds, right? So now we're learning, hey, there's actually a whole other dimension I can add to this, a whole other parameter, t, which can make this curve have motion to it. So in general, when we were in algebra, we would do this, right? This is algebra, this is pre-calc. Although technically parametrics are a pre-calculus topic, this particular portion of today is technically pre-calculus, but a lot of pre-calculus teachers don't have the time to cover it, or they don't cover it as fully as they need to. So that's why we're covering it now. It's in your calc or pre-calc book. If you go find it, you'll see it. It's usually in there somewhere, but almost nobody ever covers it anymore. So, all right, is that good? So this is algebra and pre-calculus. This is Calc 2 and 3. And it's really in Calc 3 heavily. Calc 2 is just in this one section, but in Calc 3 it's all over the place. So you take your parameter and you define it in two separate ways to create a new function that would have motion in it. Okay, so the basics of it is we're going to take a parameter, define x and y in terms of that parameter. It will make new curves that have motion, right? And this has tremendous value for physics and calculus 3, like tremendous value. Now let's go use this to analyze a familiar friend, and it should hopefully help us see how this gets set and how we use it.